discussed about sedimentary structures. So it was weathering, erosion, then you transport the sediments and you start building the bed, grading through bed forms or eroding the bed. Okay. So a lot of things, and they were at the last lecture we had a few more slides. Remember me to turn on the microphone so you'll have this recorded. We finished kind of stop here to some structures that we have as erosional structures at the bottom of the bed. And here it's the flow itself because of the turbulence making some holes, some dims in the substrate, which then are preserved as a mold. And we see them like this at the bottom of the bed, sandstone bed. And that's giving us a flow direction. So, I mean, you can do that in a stream, or you saw it, or you'll see it from now on. You have a dip in the substrate. It tends to kind of shallow up and open downstream. Think about what's happening behind the boulder in the stream. You have a hole, and that hole is getting shallower, kind of dissipating downstream. Same thing with these features, but you have to see this as a mold, so it's an imprint of it. Then there are other structures. We call them tool marks. Some people call them drag marks, grooves. These are made by things that kind of drag the flow, so they kind of scrap the bottom. And then the sediment is covering that, and again you have like a mold here. So which way the flow is going here? Any idea? Someone say up? Just say loud so we close the question here. It's up or down. We're not sure about exact direction. We have just kind of a sense in a way. I mean, you're saying, well, it's going up or down. So they're not, I mean, they're still good indicators, but then you might need other things to say about it. Other structures we see is something we call it rippled. So they're mud plast. You see a person there, it can be quite large, 30, 40 centimeters, but more commonly they're small, like pebble size, made of mud. So how it happened that you have a stream, mud made kind of pebble size plast? Well, this indicates erosion. It's erosion of a substrate or the bank in the stream. And if the substrate and the banks are muddy and a bit cohesive, then these parts kind of roll in the flow and they're deposited as mud pebbles, or they call it sometimes rippled plast because they're eroded from the substrate. An important set of sedimentary structures, but then they're given by the organism. They're trace fossils, so traces of the organisms living on a substrate, or sometimes they're digging into the sediment. So here you have examples, some of these shells here. I'm not sure what this can be. They're not oysters, they're some mussels or things. When they dig into the substrate, they will make this kind of structure. It's called Protovirgularia. I'm not sure if it's named here, but each of these will have different names. This will be Thalassinoides. So this will be kind of like holes that can be vertical, horizontal, where the shrimp or any other worms, they dig in the substrate, go after the food, they eat the organics that kind of mix with the sediment, and they tell us what type of the environment was there. Was it the lacustrine? Was it marine? What the salinity was, because some of the organisms, they like more salty environment, some of them less. So, and there are many forms of this. I mean, easy to think. These tracks of, here I think want to be dinosaurs just to make us happy about it, but it can be any, mammals or any organism on the surface. And this is kind of the surface of the bed. Different organisms, they make different type of structures. Here you have a rippled surface, with ripples from sediment transport, but it was something, an organism that they were kind of walking or whatever was doing, flipping, swimming above the substrate and give us that pattern. Here name, all of these things are named because people like to look at them and describe, this might be Krosiana hole. Right? So this like tire, like bicycle tire tracks. They're not that, they're quite old. So again, all of this can be 3D sense. So someone here was drawing it like a block diagram. Some of these things that we call again talashnoides, and they can be quite large, these things. You see a lot of things when you walk around here on the rocks. It's kind of paved our campus or sometimes on the buildings. You'll see things more like that, kind of irregular, but sometimes you see them more clearly like tubes within usually on the bedding plane of the rock blocks they use around here. So that's called bioturbation. Okay. So they're trace fossils. Around campus, these are trace fossils of Cretaceous age that were living in a sea in probably in Texas or in our area. Again, a lot of different shapes and texture. These are just on the bedding plane. And some of them are these hexagonal things. When first they saw that on the rock, they thought, well, maybe aliens or something strange, happening to be so regular. But no, these are just very deep water, like bottom of the ocean, like colonies of organisms, and they let up traces like that. So they're not fossils. That's why we call them trace fossils. So they're made by an organism, but we record just a trace of it. It's not a hard shell. So this bioturbation is telling us something else. See here, it's, let's say, a layering. It's in the core, a layer of sediments. You see it very thin bedded. But here, this is how you see if you slice a rock in the core. See, this will be barrows here, like the circular things. We see them just sliced now. So which one you think is higher depositional rate, to the right or to the left? Say louder. Right. To the right? No, I think it's to the left. So the idea is this. If the sedimentation is going slow, it's a higher chance that you have organisms living on that substrate and kind of reworking it or mixing it up. If the sedimentation is fast, you can put in a flow event like we have today, downstream somewhere, maybe you accumulate half-meter sediments from the stream. And if it's just one day, there will not be organisms that will be able to disturb all of that thickness. I mean, there are a lot of exceptions, but in general, when you see a lot of bioturbation, that means it's so intense because maybe the sedimentation rate was slower, the accumulation rate. Okay. So there are other types of sedimentary structures that they're called soft sediment deformation. So sometimes you see a bed like you have here, or zoom into the top, which is kind of, it's not, the boundaries, especially the lower one, is not horizontal, but is deformed like that. So how that happens is you put the sediment on a substrate, but it has still a lot of water in the pores and is not consolidated. And so it's easy to deform it. And if below has a muddy layer that it has the same, it's kind of unconsolidated with a lot of water in the pore, you can think about something fluffy. Okay. If you put sand layer at the top, it will tend to sink or deform the underlying bed. And then you have all of this, what we call soft sediment deformations. And they're coming in different shapes, and they're called different things like load structures. So it's the top bed that its weight, it's actually sinking into the substrate because of the loading. The weight of the sediment tend to kind of sink and deform what's below. Sometimes they call flame structures when you see more of the, let's say, mud below, kind of going up and kind of dispersing. So it's a bit of a descriptive thing, but the same thing. It's soft sediment deformation. All of the different type of deformation. Okay? And emphasize the idea that the sediments We're soft, still uncemented, unconsolidated, and prone to deformation. So it's because of the loading, or if you have an earthquake. Okay, an earthquake will just start shaking the whole basin, sediments included, and then the water will tend to go up. And while doing that, we'll also take the sediments with it and will deform the sediment if the sediment is unconsolidated. So how these things happen, so there are other words here, dish structures, for example. So in the sediment here, this is a view from a side. Within the rock, you see there are these things that it's like a thin layer here, but it's kind of going up like that. And you can see different levels where that might happen. So what is happening is when the water is going up, it's taking some of the fine grains and take it wherever it has some space between the larger grain spores, and it's giving us these structures. And they call them dish structures because if you look on the bedding plane, at the surface, they tend to be kind of circular. Okay. From the side, you see them just like this. But if you look on the bedding plane, this eventually will be kind of circular. And someone had the idea to call them like that. Okay. If this the same process, but if the sediment is kind of going up for longer, more within the upper bed, and they form these elongated structures, they can be called pillar structures or pipes. It's the same idea. The water from the underlying substrate is getting up, and it's taking some finer sediments with it, and it's giving us the structure. Liquefaction. So this is similar to that kind of loading or dewatering that I show you first, but we see the deformation within the bed itself rather than just at the bottom. So let's say here was the horizontal bedded, horizontal laminated bed, and then the water again was going through, the sediment was still unconsolidated, loose, and then is deforming those horizontal laminations within the bed. Okay. So these beds, we call them convoluted bedding or convoluted beds. So it's kind of strange structures that you see like that. And the processes producing this is this liquefaction. And again, an earthshake will do that. So if you have an earthshake and the sediments have a lot of water in the pores, they're unconsolidated, when you do that, the water from the pores will tend to go up because of the kind of mechanical compaction and is disturbing any lines. Sometimes when more of this happening at the larger scale, you might have, for example, sand here, somewhere deeper with the mud above, and the same thing from the loading of the sediments, or again an earthquake or some sort, but most common is just from the loading. The water where the fluids are going up through the mud, and sometimes taking even the sands with it because it's making this kind of larger conduits, like pipes, and they're coming at the surface and make what people start calling mud volcano if it's mud coming up, or sand pipes or sand volcanoes. So really, you see them like spewing like out of water and sediments at the top here. But these are really small, like 10 centimeter scale there. And this happening just because of the loading and the pressure coming up. But again, like at small scale here, just bed scale or a few beds. Questions about this? These are strange structures. The one that they're more commonly seen or used are those bed forms, ripples. When we see the bed is building up. But all of these other structures, deformation, trace fossils, float casts, they're giving us additional information on how we should interpret the rocks, which environment they were deposited. let's see what we do here. Now we really get into a different topic, or actually two topics, because of that freeze that holds us out of classes. I combine this. We'll discuss as much as we can of these topics, and I didn't take many slides out because I don't want you to be less prepared than your colleagues last year. But for the test, you will have the material wherever we stop. So for the rock classification, you should already know from other classes that their coarse grain, we call them conglomerate. As you have an example here, this stick is about 1 meter of a scale, and they're heavily beds that we call them conglomerates when they're lithified. And then there are sands that when they lithify, call them sandstones, and there are muds that when they again lithify and turn into rocks, we call them mudstones. And we'll see there are ways to actually classify these things. You saw this already. This is a table showing the different grain sizes, and this is key when we classify this clastic rocks. Okay, things to remember: 62 nanometers. That's the boundary between what we call mudstones and sandstones. If the grains are larger than 2 millimeters, then we start calling them conglomerates. And of course, for different size of the grains, we have different names here. Okay, so just to know that. Remember how to get into this, you just double the 62. So 125 microns, you go from very fine sand to fine sand. Next class, double that to 50 microns, you go into medium sand, so forth. Okay? Now, probably not only geologists, but in geology, you'll see a lot of these ternary diagrams. Do you know how to read that and what it means? Some of you say yes. Everyone say yes? Thank you. So then we can skip it, half of this lecture. Maybe not. But it's explaining us a mixing between three materials. So if you have just two, I still have to go fast over this. So between gravel and mud, here is 100% gravel. Here the line of 80%. Here it's 0% gravel, but it's 100% mud. And you do this between all of these three, and then according to what concentration you have, then you call the rocks different names. Again, it's very coarse here. If it's mostly gravel, we call the rock conglomerate. The conglomerate, the large class, can be, if it's more than 30% of this class, then we call it conglomerate. But then you can have so many large classes, they touch each other, and then it's called class supported. An image might be here, but you might have a lot of smaller material between the larger class, and then you call that matrix supported. Matrix is called all the material smaller sizes between the larger class. Matrix. I think these guys were using the word before the movie show. This is a matrix support. Okay? So then you can have conglomerates, sandstone, mudstone, or within your conglomerate there are a lot of mud. Maybe it's this matrix, you call it muddy conglomerate, sandy conglomerate. Okay? Here it is. You have this, how to read this. You go there, 65. You go there, and this may be 30% mud into that sample, and then maybe 10% or 5 of sand, so you call that the muddy conglomerate. And if you have a rock with this kind of proportions here, 65, 13, 5%. Good. Now, if you look at, without the conglomerate now, you just look at the finer grains, and then you can do diagrams between clays, silts, and sand. And you wouldn't see this word here like sandy, silty clay kind of word, or silty clay sand descriptions, unless you work for, let's say, USGS and you have to do reports, or if you're a soil scientist. So they really get into this detail naming of the rocks. Okay? I mean, I will also get confused. If you don't work much with that, you might not remember. But it's a logic way to do it. Clays or sands or silt is just at the corner. So if you have more than 80% of that material, you call it what it is. And then if you are mostly between, two of the materials, sand and silt, you call it silty sand if it's closer to sand, sandy silt if you're closer to silt. And then if you start adding clays, you add clays to the description. Okay? Well, I'm showing you just to know that you have all of this classification. So you just call it sandstone, siltstone. Probably most of your work you'll do. And then if you feel it's a mix, you might get into sandy silts. However, this is the more important or interesting way to describe now maybe just the sands. People look more at sands because like reservoirs are more, easier to see the grains and kind of describe them. It's based on the composition of the sands. What type of grains are making the sands? And they thought, well, quartz is common, so we have quartz in a lot of rocks. Then you can have feldspar. Remember one of the silicates that maybe you know from the intro class? And then lithic. And lithic is any other type of grain. It can be a grain made of like mud. Just muds that are rotted off, and it will be lithic. Or maybe a volcanic crust or grain, and then it's in the lithic. So it's quartz, feldspar, lithics. And now, the names, I know they're new, and you might have to kind of remember a bit, or just know what is called. This arenite thing, it actually means sand. It's coming from Latin. So a lot of people, when they start describing these things, they're using Latin words to describe that. So quartz, some people just call it quartz sand, but in the books you'll see it as arenite. It means just sand. Now, they use Arcos word for when most of the grains are feldspar, okay, with some lithics up to 25% and up to 25% quartz is Arcos. And then if there's mostly lithics or grains of different type of rocks, they're called, but not quartz or feldspar minerals, it's called lith, from lithic arenite, which means kind of sand. And that's why. But let's see how we recognize some of these typical grains, because that's important for you to know. So before we get into that, we have a more complicated way to see that, but it's the same as you saw before. Quartz in one corner of our triangle, feldspar, and lithic. Was on the previous slides I didn't mention, was a faculty here, Bob Falk. He passed away recently, just finished a few years back. That he was working on this classification in the 50s and 60s, so he was a well-known person for working on these things. He did a lot of microscopy, so he was describing rocks with the microscope. But here, once you do this triangle, the question is, okay, this is for sand, but what's happening if you have some muds into it? And the muds were kind of depicted here on the other axis. Okay. And the mud, because they're smaller particles, they call it matrix here. So if it's mostly sand here, like 90%, 95% of the grains are sands, you call that arenites, that means sands. Again, they use this strange word. If you start having mud mixed with that, you call that wakis. So you can have a quartz waki if you have 80% sand and 20% mud, let's say. Then if you have more than 50% mud, you start calling them mudstone. the dominant. So just to know that it's a strange word, this wackies, like lithic wackies or feldspathic wackies or quartz, when you have a mix of sand and mud, but still sand dominant. Now we get, and I will show you photos of this, like quartz grains, feldspar grains, and lithic grains. It's quite easy to separate it into these three classes under the microscope. We have no lab, and I mean even the time for geology majors, you know, the microscopy time lab, someone told me kind of decreased. They're not shown too much of it, but it's nice to see, look at the photos that you'll see under the microscope, how to differentiate these three classes. It's important even for you because what type of grains we have, it's important for reservoir, for the cements in the reservoirs, for how the grains maybe were dissolved or were exposed to diagenetic processes. So I'm not sure if you per se will look at these things, but I'm sure you'll see reports within the companies that they discuss what type of sedimentary rocks the reservoir is made of, down to the grain, let's say, mineralogy properties. So, quartz, feldspar, lithics, these are images. So the quartz, there will be from white to black tones of grain under the microscope. Feldspars will have this twinning thing, so there will be lines of dark and lighter color. And the lithics will be a mixture of different grains and different patterns, will be sometimes small crystals part of it. So why we can see that at the microscope is we have something that's called polarized light. You know about that from physics and other classes? Some of you say yes. Everyone knows about it? Good that you say no, so I can go a bit slower. So the thing is this, the normal light that's coming to us, it's going in all directions like that. Okay. But then you can put some filters and you have the light polarized, what is called, so it's going only up the one direction here. So you just kind of up, down here. So you just select the wavelength that's going according to one direction. So when you do that, you know what direction your light is going. And then from an ordinary light, through your filter at the microscope, you let the light going up to one direction. But now, if you have a mineral, very thin slice of mineral, that makes it transparent to light onto the microscope, and you start rotating that mineral. Okay? So at one point, we'll have no light passing through, because this wavelength direction of the light, it's kind of stopped or interfering with the crystal orientation of the atom orientation within the crystals. So you have no light, so your mineral will show to be dark. And then you keep rotating your crystals, and the light will pass again through it. So the distance between, the angle of rotation between no light and light passing through is giving you those angles of atoms orientation in the crystal. So you know what type of crystal it is. Okay, when the crystallography, I think they're measuring some of those angles between the crystal and things like that. So you use this a lot for the mineral recognition, because these angles are well known for different minerals. So that's why the photos I will show you will be this different colors, gray colors from white to dark. Okay, different shades. So here will be a quartz example with the calcite cement. This is the cement, these are the grains. And the scale here, you have 100 microns at the bottom. Okay, so just to know what this would be size. So if you want to think from here to there, might be 300-400 microns. That would be medium sand, according to our classification. Okay. So what's happening, this is ordinary light that we call OL here. if you make it polarized light, some of the grains will appear darker, some of them almost black. And that's because their crystallographic axis is at an angle now relative to the light. And according to that, they will go what we call extinct, like black, or they stay white. And if this will be under the microscope, and we'll start rotating this one will turn white, this will turn dark, according to how much we rotate the plate. There are other examples. So this is ordinary light of a feldspar, and will look just white because it's transparent. When you put the polarized light, you start seeing these lines of white and darker bands. This is twinning, so it's telling us about the crystallography of the mineral, and we recognize it is at that angle. I'm not sure, it should be what, 89 or so degrees here, and then a bit more given the sun. And it's telling us it's a feldspar. But this twinning is what is typical. Another example, ordinary light feldspar, it's referring to this grain. We don't see much, it's transparent. Maybe we'll see some of these cleavage surfaces, but under the polarized light, it's appearing banded. Okay. Oh, look, there are other grains here. What this might be. Someone have a guess? Quartz, yes. So see, it looks like the previous slide. So that's what it is. A lot of this sand material, they have multiple grains, and that's what people do. Look at the microscope, start counting how many quartz grain, how many feldspar grain. And then they plot on the ternary diagram and call it a quartz arenite, or a wacke. Here was an example of ordinary light of some lithic fragments. And lithic, like I say, can be anything, like limestone, siltstone, clast. Here it's ordinary light of a siltstone. So the way we recognize this is something different is this is the grain, but it's made out of smaller particles, like clay, mud size, it all together within a clast. So we recognize it was maybe a mudstone that was eroded off, or a limestone. And now it's a sand-sized particle. Again, the scale here is 100 microns. This is a silt, and appearing dark even through ordinary light, because there are a lot of small grains that they kind of let the light or reflect the light according to multiple directions. But because there are so many grains, each of them in different directions, it's coming opaque or dark here. As a siltstone plastic. So another example here, a siltstone clast, that they say scale is smaller now, 50 microns. So it's a grain, but it's made out of other smaller grains then. This is the same class now through polarized light to emphasize that there are multiple smaller grains that's making this. Yes? Which one?
If you go back, you can see that.
Yeah. Well, so this might be, I mean, sometimes they're real from the rocks and can be fluid inclusions. You know, if it was like a larger pore, it may have some fluids, and it's giving you strange things. However, it depends how the thin slice was made. It might be just from the way they made the thin slice, you know. They have to cut, I forgot what is, maybe 10 or 20 microns thick. When you do that, to be sure you allow the light to pass through, and then you put in a resin. See all of the blue things that you see around, they put the dye into the resin or the glue to keep the thin section. Sometimes they have bubble of air, things like that. Maybe a long explanation there, but that's what it is. And it's interesting about this blue. So when you see photos with blue, usually that means pores. And they put the dye in it to be easier to see the pores, so things that they're not, clasts and things like that. Forgot to mention that. Another example of a lithic fragment, but from a metamorphic rock clast. So there are different minerals here. You don't have to recognize beyond saying, well, this is a lithic fragment. Okay? And here there are some volcanic clasts. And still we call that lithics. We don't get into the detail, what type of volcanic rocks coming from, things like that. For the classification reasons, we don't need that. And then next is to go into the finer grain rocks and what we call the mud. Or if it's a rock, it's a consolidated, we call it mud rocks. And we continue to do the size of the clast. So if they're smaller now than 62 microns, we call them silts. If the grains are even smaller than 3.9 microns, it's really difficult to see that with the normal eye. We call them clay or clay stones. So because we don't usually look into this separation when you look at the rocks, in your hand, like a hand sample, we just call them muds, and we're lumping the two together. But if you know that most of the clasts are silt size, then you might want to call it a siltstone. Sometimes you heard this like shells. So the shell would be fissile clays or clay rocks. So the one that kind of tend to break along a bedding plane or a surface. So just briefly on the clay minerals, I think you know this from some of the intro classes that a lot of clay minerals are silicates, and then they have this layering organization of the crystals. For us here, what is interesting is this, that the clays are a weathering product of different type of other silicates here. So when the rocks are coming at the surface, like volcanic rocks, for example, or metamorphic rocks, they have a lot of silicate minerals, but at the surface, at the temperature and pressure at the surface, and through the reaction with water, they're becoming stable. And they change their mineralogy into different type of clay minerals. I have some names here. We'll go over some of the names like kaolinite, smectite, okay. So, and these are different, they have different elements within them in their composition. A lot of them have aluminium, but then there are other elements as well. So what is important is that they have they're chemically complex with different atoms, like I say, but they have large surface areas for reactions. Okay, because they're organized like sheets like that. They can react easily with other, with the fluids or any other type of reactants. And then for the hydrocarbon, there might be a source rock, and that's because it's a lot of organic material between this sheet or sticking in between the clays. So here there are images at the SAM, that is scanning electron microscope, and maybe you saw some of this before. So this will be some of this clay particles or minerals. The SAM image is not, what we see there is not the light actually. It's a beam of electrons that's bouncing from different surfaces of the crystals. And with bouncing more, we see kind of lighter gray here. Less bouncing of that beam of electrons, darker. So they look like they're illuminated, but the light is a beam of electrons that's bouncing back to us. So they will be like sheets like that, and they're hydrated, so they have a lot of water within their composition. Well, I will just mention some of the names so you know about this, and some of the interesting properties are used for this materials. So it's something that's called kaolinites or kaolin group. There's a different name of the minerals. It's enough maybe if you think, oh, it's a mineral or clay mineral called kaolinite. And they have aluminium in their composition. It's a weathering product that you find in the soils. And in some places, the kaolinite accumulate thick enough and in large volumes that can be mined with trucks. Okay? And that material then is used in porcelain, the ceramics. And that's what they put in our toothpaste. What do you think the toothpaste is made of? I was using it this morning, but sure. That whitish, and sometimes they put color. Or it's just this clay. They put some flavor to it. I know, difficult to believe that, but that's what they do in a lot of things, okay? The cosmetics and things. Just clay material. Go dig it out. I'm not sure if they wash it, whatever they dig in quarry, but then they make the toothpaste. You don't feel that the grain is there because they're so small. There will be microns that will feel like kind of smooth and things like that. Then there are other clays called elites, for example, or glauconite. Glauconite is underlined here. It's important for environmental reconstructions. So this will have aluminium, like all of this clays, but they have other elements to it. The elite, sometimes in ceramic material or building material, is used. Okay. Chloride, the chloride groups it's a byproduct of the weathering of some of those mafic minerals. If you remember some of this word from intro class, pyroxene, amphiboles, biotite. All of this, when they weather, you'll have magnesium and iron in the composition, and then all of that magnesium and iron is what is within the clay formula there. Okay, all of these clays, they have this sheet shape and as a crystal. Okay, so you look here. A rock wouldn't look much, but if you look at the SEM microscope, then you will start seeing the shape of the crystals. The smectites group, strange names. Again, if you remember one, would be good. From this list of montmorillonite, bentonite, and nontronite, bentonite is important for you to remember. Maybe you already heard that. They use bentonite, which is again the weathering product from volcanic rocks or clay. It's used for drilling. So the bentonite, what he's saying here, it's used for drilling, mud drilling, landfill liners, well pump plugs. So why is that, you think? Why they use clays for landfill liners? It's low permeability, but more than that, you put it dry, around your ponds. If the water is getting through the soil and hitting this bentonite material, it's expanding. And when it's expanding, it's becoming impermeable. Okay, so it's like a plug, kind of natural plug. Now, why would they use this for drilling, do you think? Well, I think a lot of slides to get through, but because it's important for you, I can mention more of this, is you put bentonite into your drilling fluid because it's expanding when it's hitting the water. So if you have that in as a drilling fluid, if you hit an aquifer, instead to lose your fluid all the way into the aquifer because of the pressure, you have bentonite. So the bentonite's coming, hitting the water, what's doing? It's expanding, plugging your aquifer, so you don't lose your fluid anymore. So in some cases when drillers know what's coming to them, or it happened in the previous hole, they use different material and sometimes put a lot of this bentonite, just bags of clays, into the drilling mud. Here it's another one question, kind of following up. How do they use bentonite in the drilling fluid? Because the drilling fluid is made of what? Mud, but how do you make the mud? With water? So, but then wouldn't bentonite will just expand in the water? No, they don't use water. They mix the bentonite with kind of hydrocarbon products. So they use less water within the fluid mud, with this idea that you need to use the bentonite to actually plug your holes. So there's, I hope you know more than just this story from your other classes in engineering. Okay? But just to remember bentonite, when you hear it, like, whoa, I know about this strange clay material. And again, this is just naturally occurring in just a byproduct of weathering volcanic rocks. Oh, what's this? Oh, what is a sedimentary rock? Okay, this is the next set of slides. So questions about rocks, classifications. You just go by the size. Watch out for the signs. They look at actually what mineralogical composition is made of. And then the strange different names they use at times. And that's because people look for more than 100 years into these things and everyone wants to name something. But it is a logic behind the classification, so try to remember as much as you can of that. Now, again, what is a sedimentary rock? It's sediments that turn into a lithified material called rocks. And with sediment that we're talking so far, it's something called diagenesis, which is any physical, chemical, biological alteration of sediments right after you deposit them. And part of that is lithification. But even after you lithify, you turn it into rock, you still have these processes acting on your rock now, and that's still part of the diagenesis, what is called. So, lithification is a conversion of loose sediment into the rock. So how do we do that? How do we have loose grains that they start sticking together? What's happening? I mean, lithification, but how that's... Okay. Say louder. Pressure is just compacting them. So you need a cement. You need new material between the grains that kind of start precipitating, and then it's kind of locking them as a rock. Okay? So that's part of the diagenesis as well. So the result of this is this lithification. Again, you can see it now as cementation, but again, in the textbook it's called lithification. So the cement. And then you can have a reduction in porosity because of compaction, because of dissolution of some materials, or you can have a production of secondary porosity. That means you might have a porosity larger than you started with through dissolution of some of the grains, and dissolving some of the material. Okay, let's get over what this diagenesis is. So once you have the sediments accumulating with the surface, let's say you're at the surface here, the pressure is increasing with depth. Okay, so you have depth on the right axis, and you can see depth also as respective to the pressure. Deeper you put the sediments into the substrate, higher the pressure. Now, with the burial, it's also the temperature that's increasing. And then that's what you have here on the top axis. Let's say 0, it's not quite 0, maybe 20 degrees at the top, 10, 5, depends where you are on the Earth's surface. But with the depth, you're increasing the temperature here. The diagenesis that we're discussing is about within this triangle here. So we're talking about the sediments getting down to maybe 15 to 20 kilometers depth, and with pressure about this 5 kilobars, and the temperatures up to maybe 200, 250 Celsius. What's happening if you bury deeper than that, or the temperature is getting higher? You have, what's this called? Metamorphism. What that means, do you remember? It's melting. It's not quite melting yet, but the crystals, they're changing their properties. They turn into a different type of minerals, called the grains. So if it's too high temperature, too high pressure, you have different type of what they call here metamorphism. So some of the let's say, clay material, they start turning into other type of so we cannot talk about whatever was at the surface, like sediments anymore. So we'll stay here. What is a typical temperature gradient in the Earth's surface? You should remember that. You'll probably hear it in multiple classes. It is about this. If you drill a hole, if you go 1 kilometer down into the Earth's surface, what temperature you expect for 1 kilometer down? Let's say 5 kilometers down. What temperature you expect? Yeah, it's about 30 degrees Celsius per kilometer. Or for me, it's easier to remember 3 degrees per 100 meters. So if you have a well that's down to 5 kilometers, a normal, I say normal thermal gradient, will be about 150 degrees. Sometimes the gradient is higher, and then this curve might be kind of less steep here. So then you hit higher temperature. That's where they go after that geothermal energy. If you have a higher thermal gradient, you want to know it first because your drilling might adjust to that, but also because the fluids there will be warmer than you expect. You might want to make sense of that. Then it's something else that here is this geostatic gradient. So with depth, like I say, the pressure is increasing, and this is normal geostatic gradient. So this is just the weight of the sediments themselves. So if you drill a hole, you know what fluid pressure will have on a given depth because of the weight that is on those fluids. Okay, so that's giving us, let's say, the geostatic pressure gradient. And that is important because now you have two types of pressures coming. So one is the geostatic, so the gradient, this is the pressure of the rocks. And then you have the hydrostatic gradient, so just the weight of the fluids themselves. You know, if in the ocean, this will be your pressure. But because the rocks are heavier, then you have a steeper gradient, so it will be higher pressure. Keep on like that. So these are just what it's happening if you have a normal pile of sediments with the fluids getting, a water column all through the pores, all through the surface. That's what you expect. Now, we discussed this already. If you have a sediment from the surface, you keep accumulating them. They start with the porosity, which for sandstone, let's say, is like 40 here. Some people put it higher, 50. For shells, it's a higher porosity at the surface, up to 70. So why the shells are more porous? They're smaller grains to place, but why would they have higher porosity? Should come easy to you. Because what's the shape of the clay? You know, like sheets, remember? And then they come kind of strange angles. So it's more pore space in between these sheets. But then it's easy when you put weight onto them to lose that space. It's easier to compact those sheet minerals. And that's why even if they have high porosity, 70% means 70% space between your grains or the minerals. Okay? But look at the surface, even, what's this in kilometers? Yeah, okay. So at the surface, fast you're compacting those grains, and you come to lower porosities. The same thing happening with sands. How that is happening, again, the grains here are depicted as without the size, but let's think sands. They're kind of loose, you put weight, you compact them, and you get, closer packed. So when that's happening, what's happening with the fluids in the pores of this material? What's happening with the fluids? They're moving up. You have to expose them from here, and they will migrate somewhere else through the rock. You have to have that in mind. So, okay, you compact, but you compact with losing porosity, or you're losing the pores. The fluids there have to go somewhere. And so the fluids are migrating when you compact the rocks. And that's what's giving us some of those sedimentary structure we're talking, was because you compact them close to the surface, so the fluids will just tend to go up the easiest way. Will be a problem if you're deeper into the earth. When you start compacting the rocks, you might have an impermeable layer at the top. So the fluids wouldn't be able to go up. So where would they go? Wherever they can. They can migrate laterally, they can migrate even down. Okay. So, per fluid they're expelled. So here it's another graph to emphasize the same kind of curves. You have high porosity at the top here for both sands, muds, shells, limestone. With the depth, you decrease that porosity. Why I put this one here is because we have references there, you can look at the papers, but it's a formulation. So we know at the given depth for a given lithology, we know what porosity we expect. So we have the porosity theta 0 here, phi 0 the surface, and then we have here Z is the depth, and there's some coefficient for different type of lithologies. And then you can calculate the expected porosity at the given depth. Okay. Now, here it is the idea that the muds, they compact more, I say, at the surface. If you have everything the same porosity, or the thickness with the pores of sands and muds, it's not the same porosity, sorry, it's the same thickness, but the porosity will be higher in the mud. Remember, maybe 70% highest. Sands just 50%. And then when you load them, which one will compact more? Muds, because again, it's easier to lose that porosity to compaction. So because of that, you kind of change the relative thickness to each other. But what you do when you're losing all of this thickness, you compact let's say the solid material, but the fluids will go out. So when you compact anything from 41 porosity to 37, look, you're putting out the fluids. Okay? And that's important for a process. It's called sometimes overpressure. And maybe you heard that in some other classes. So here's the story. Let's see if I can explain it correctly and you can remember this from now on. So this is a compaction curve from the surface. So you have some porosity here, and then with depth, this will be what's expected. But at the given depth, well, the porosity kind of stay high and is not decreasing anymore. So what that's telling us about the rocks, if the porosity, even if you increase the depth and increase the pressure, but you can't compact them anymore. So and that's what's telling us, the porosity kind of stays the same, you can't decrease it anymore, even if you increase the weight. Okay, so that's what it's telling here. You're compacting because of the weight, but at one point, even if you expect for the rocks to lose that pores, it doesn't happen. It kind of stay the same. So when you do that, you increase the pressure within your fluids in the rocks. And you see that on the hydrostatic curve. Again, from the surface, with the depth, you increase the hydrostatic pressure because you pile, let's say, more and more material above. So this is what you expect the pressure to be in the pores. If the pores will be all the way connected to the surface. But at this depth, they're not. So you're increasing the loading, but the pores will have no way to expel their fluids out to accommodate the weight. So at this given depth here, what the curves are telling us, well, the pressure is increasing, but hey, look, the pores stay the same, the rock's not compacting anymore, and the consequence of that is that the pressure is higher than it's supposed to be. The fluid cannot go up. Right? So here it's an examples of such observations. To the left, you have a diagram with the porosity measured within the rocks here. It's ODP, it's Ocean Drilling Project or something like that, an international consortia. They go around the ocean, around the world and drill holes in the ocean, measure different things for science. And here it's a depth down to 800 meters. And here's the pores. They start 70%, what they measure in the rocks. The depth, there are some higher areas. And this is a trend that's supposed to be according to the depth that you expect. But you have higher porosity at the given areas. And that's why you expect also higher pressures. Now, this is a graph to show you that it's not so easy, even if you think, well, yeah, we know all of these equations. These are porosities measured at the Gulf of Mexico, Texas Gulf Coast, and many wells. Right? And here with the depth, that's what they're reporting it here. Okay, so here's the porosity scale. Well, at the surface, yeah, they're higher, it's higher porosity, and then overall it seems to decrease with the depth. But they're scattered all around there. Okay, so some of them, yeah, maybe in theory it should be like that, but then it's more scattered. Why is that, you think? Because, again, there might be some of them might have hit this overpressure at different given depth. I mean, the way to expand or to expose the fluids out of the pores and compact them, it might stop at given depth. Okay, so then you end up with a higher than expected. But then you'll see when we discuss diagenesis, you might start cementing the grains. So you fill the pores with the cement at the relative shallower depths, and then you decrease the porosity faster than just the mechanical compaction. Okay, so there are some other processes, like chemical processes, that decrease our porosity. Okay, I think that was it. So we get a bit into more than mechanical compaction. So here it is. The easy way to see is this from cubic packing, so the grains that slightly touch. When you increase the compaction, they rearrange into this maybe rhombohedral packing. So you decrease the porosity by just moving the grains a bit. Here depicted as spheres. What else is happening? The next is that, so A and B is this just compaction. Another things can happen is that you start deforming the grains. Okay, so you can break them. If you break them, then with that deformation, sometimes the grains are just bending a bit, but you decrease the porosity by doing that. Another thing is you'll see is what they call concavo-convex contact. So some of the grains actually start dissolving because of the high pressure at the contact. And by doing that, you decrease the porosity as well. Okay. Or some of them, when they dissolute or dissolve more, then you have this structured contact, what is called here. show you some examples of this. So here we call them photomicrographs. They're just photos taken out of the microscope. But here it's a feldspar grain that was kind of broken down, fractured by the pressure. Here it's a mica grain that kind of bended because of the higher pressure. So all of this happening, and the grains, they come closer to each other, the porosity is decreasing. Notice that the blue here, like I said earlier, this is just pore space, empty space. So they use that dye when they make the thin sections to be easier for us to follow. So the pressure solution, so what's happening at the contact between two grains like that, it's a higher pressure, and then maybe the grains are deformed and then more prone to reaction with the fluids in the pores, and that's happening right where the contact is, and then by doing that they're increasing the reaction along the line, in this case dissolution. And here are the examples of this. You see this grain here, it would not be so well kind of sutured here and ingrained with the other grain if this dissolution didn't happen along the surface. Right? So initially they were more loose and probably just one point contact. So all of these contacts here happen through this dissolution. Sometimes they are called concave or convex contacts because one grain it's concave, the other one convex. A good indicator of this process is when you have things called stilolite. And this is just a suture boundary, but it's more visible by some of the material that was left behind. You know, when you have two grains, they dissolve, but there are other components within the grain that they will not dissolve. So they stay behind and kind of depict here, it's a microscope, kind of the suture zone is like this drawn there. Okay, so we know this mineral was bigger, the other one was bigger, and both kind of dissolved. To make the suture zone, and when you see it with the material, you call it a stilolite. Like that. Now, we'll go over some of these things. They're chemical processes in the rocks. So the more important is cementation. So it's a precipitation of the mineral that cement the rocks. And this is happening in the pores. You know, they precipitate from the fluids. The opposite can happen. It's a dissolution, dissolving the mineral, and it's creating secondary porosity. Orthogenesis, it means it's genesis of the new minerals. That's what it means. The genesis of the new minerals, ortho. Or sometimes it's recrystallization. So you have a crystal grain is dissolving, but is precipitating the same material. Okay. Or replacement. You dissolve a grain of quartz and you precipitate calcite instead. But it's the same kind of space of the previous grain. So that means replacement. You replace the grain but with different material. So here we go over some examples of cements. Okay. The cements can be made of a carbonate material, calcite or aragonite, or silicates, the most common material. And where does cement or cementation happen? Within the pores here. And you have an example here with the pore with all of these lines around the grains will be small crystals that they start drawing on the edges within toward the pores. When that's happening, you see that it's kind of suture the grains also. And that's how they lithify sediments and turn into rock. Okay? Now, the carbonates and the silica material, they precipitate at different under different conditions. And pH is maybe important and easier for you to remember. So if the pH is alkaline, higher than 7, it's the carbonates that precipitate, calcite, aragonite. If the pH is acid, lower than 7, it's the silica that's like to precipitate. So then it depends what material you have dissolved in your fluids and what pH that has. If you change the pH, let's say with fluids with depth, how will you do that? Well, through the pores, the fluids are moving because of this differential pressure. So when you do that, you move, fluids with different properties through the rocks, and they might change the pH. So in some parts they dissolve the silica material, but they precipitate along as they migrate. They precipitate, they form the cements. So here it's a graph to show the same idea, that you have, again, a pH scale here, and then the solubility on the vertical axis. So according to the pH, you might have the quartz, it's increasing the solubility with the pH. The calcite it's decreasing with the pH. So again, opposite conditions. On the lower graph, it's showing the same with the pH on the x-axis. On the vertical axis is what they call EH, or oxygen reduction conditions. So you have other type of minerals like pyrites, yellites, glauconite, some type of clays that precipitate if you change the oxygenation condition or reduction. So these are type of the minerals that you'll find within your pores that might close your pores to cementation. So there are examples of calcite cement, of which solubility is decreasing with increasing pH, temperature, and pressure. So what is important on this list of where calcite cement is dissolving, let's say at the very surface, but it can form later diagenesis with the depth. It might start actually dissolving some of the pores, some of the minerals, and forming larger pores, what is called the second